Now, when we talk about qualitative response regression models, what we actually mean is that our dependent variable, that is the y variable, is a categorical variable. The example I earlier gave you was where the y variable is the decision whether to be a part of the labor force or not. Now that is an example where your y variable is a dichotomous variable, that is, it has two categories. There are extensions of this type of response models where your y variable may be a trichotomous or a polychotomous, that is a multi-category variable. For example, suppose I'm saying that my dependent variable is my decision regarding the mode of transport. So I have this variable of mine can have three categories. It might be the choice of public transport, the choice of traveling by using a private vehicle, or the choice of using means such as the auto rickshaw to get to my destination. So what are the different variables that affect my decision regarding the mode of travel? Right? So that is an example where my y variable has more than two categories. For the purpose of our syllabus and for the purpose of understanding the qualitative response regression models and its basic features and how they are run or estimated, we are going to stick to y variables which have only two categories. Okay, but remember that all these points that we are going to discuss can be extended for more than two category variable as your dependent variable. Now, moving on to what are the possibilities or how can you estimate a model when the y variable is a categorical variable. Our regular model used to look like this: yi is equal to beta 2 xi plus ui. Now suppose y is a categorical variable where it is equal to 1 if the family has own house and is equal to 0 if it does not have an own house. Right? And in this example, I can assume that the explanatory variable xi is the family income. So my explanatory variable is a scale variable or a ratio scale variable or a quantitative variable, but my y variable or the dependent variable is a categorical variable. It can take two values. If the family owns the house in which it is living in, it's 1, and if it does not have an own house, if it does not own the house where it lives, it will be 0. Right? So in such a situation, is it possible to use an ordinary least squares method like we have been doing so far? Technically speaking, there is nothing that will stop you. It is possible for you to run the regression model in a statistical software such as SPSS or R or Stata or any other softwares, statistical softwares that you have. If you run a typical linear regression model such as this, where your y variable is a categorical variable, it is called a linear probability model. probability model, short for LPM. And as usual, your expected value of yi given xi, that is your expected mean value of yi, will be given by beta 1 plus beta 2 xi. Now, the reason it is called a linear probability model is that if we assume that the assumption regarding the error term holds, that expectation of ui is equal to 0, then our estimated value of yi given xi will be beta 1 plus beta 2 xi. Now, your yi can have two possible values, the observed yi. It can either be 0 or 1. So, if we say that pi is the probability of y being 1, then 1 minus pi is the probability of y taking the value of 0. If you observe this, the variable can have only two options. It can either be 0 or 1, and the probabilities associated with it is 1 minus pi and pi respectively. I hope that you recognize this as a Bernoulli's probability distribution. So when you have this sort of Bernoulli probability distribution, your expected value of yi can be written as 0 into 1 minus pi plus 1 into pi, which will come up to pi. So what this means is, when you run this regression as yi is equal to beta 1 plus beta 2 xi plus ui, the expected value of yi given xi will give you an estimate for the probability pi, which is a value of probability of owning a house. In this example, pi is the probability that yi takes the value. Pi is the probability that yi takes the value of 1, and it can be shown that since yi takes only two possible values, it can either be 0 or 1. The expected value of yi can be shown to be equal to pi. So if you run the linear regression probability model as beta 1 plus beta 2 xi plus ui, the expected value of yi given xi will be beta 1 plus beta 2 xi, and this will be the probability, a measure of the probability that yi has the value 1. So technically speaking, it is possible to have a categorical variable as your dependent variable and still run the regular linear regression model using the regular OLS criteria. However, there are a few things that we need to note. The first among this is that since the expectation of yi given xi is actually the probability of the dependent variable taking the value of 1, its values should lie between 0 and 1. This is because, if you remember, probability is a value that lies between 0 and 1. So that is one restriction that should be imposed on our model when we are running it using the usual OLS criteria. Now, besides this restriction, there are a few other problems that we might come across. The other problem that we might come across is that our UI or the error terms are no longer normally distributed. If you remember, UI is the deviation of observed yi from the expected or the estimated yi hat. So that is minus beta 1 minus beta 2 xi. So here ui can take only two possible values. If your yi is equal to 1, your ui will be 1 minus beta 1 minus beta 2 xi. In other words, this is the same as saying that your value is pi, and if the value of yi is equal to 0, ui's value will be 0 minus beta 1 minus beta 2 xi. So if your ui values are only taking two possible values, then they cannot be normally distributed, and your normality assumption of the error term is violated. However, if your sample size is large enough, then your OLS estimates will be unbiased even if your error term is not normally distributed. Right? But our problems with the linear probability model does not end there. Another assumption that is often violated if you try and apply the LPM is that the error terms are not homoscedastic, that is, heteroscedasticity of the error term is another problem that crops up when it comes to the linear probability model. Your variance, as I showed you in the last slide, ui takes two values with probabilities pi and 1 minus pi. So ui is following normal distribution, Bernoulli distribution. A Bernoulli distribution variable has a variance equal to the pi into 1 minus pi. That is the product of probability of success and multiplied by the probability of failure. Now, since your pi itself is dependent on or varies with the value of xi, the variance of ui will also keep varying with the value of xi. So the assumption that the variance of ui remains constant throughout the sample is violated in the case of a linear probability model. However, again, like we learned in the chapter of heteroscedasticity and its various remedies, it is possible to run a regular OLS for the linear probability model, figure out the sample estimates of the variances, and then run a weighted least squares model which takes into account, which is a GLS model, which takes into account the information that we have about the variance of the error term, and then obtain estimators which are blue. Okay, another method of course is that you can use the White's heteroscedasticity corrected standard error terms to deal with the problem of heteroscedasticity. But remember, these heteroscedasticity corrected standard errors and so on are always more valid when you have a large sample, that is, the sample size is increasing indefinitely. Okay, so again, if we have a decently large sample, maybe we can deal with the heteroscedasticity problem as well. Still, the LPM has one more problem associated with it, and that problem is that there is no reason why our probability value, which is expectation of yi given xi, exists or continues to remain between 0 and 1. Mathematically speaking, when you run this regression model, yi is equal to beta 1 plus beta 2 xi plus ui, it is possible that you will have yi values less than 0 or negative as well as greater than 1. So what do we do then? It is here that we have the most troubling point of the linear probability model. You could probably say that if the values of yi come up to be negative, you assume that it is equal to 0, and if the value is greater than 1, you can assume it to be equal to 1. However, there is not much statistical logic and mathematical logic behind these assumptions. So what is suggested instead is that you modify the estimation technique in such a way that you are guaranteed that your dependent variable which estimates the probability of yi being equal to 1 and 0. So you can devise a technique or a procedure through which these estimated probabilities lie between 0 and 1. And these techniques, there are two of them that we will be learning. One is called the logit technique. Some people also call it logit. And the second is the probit. So these two models are going to be the main subject matter that we are going to deal in these coming few lectures. There is also another model called the Tobit model, which is also a type of qualitative response regression model. Again, through this technique also we are devising or creating an estimating technique such that the conditional probabilities will always lie between 0 and 1. However, from the point of view of our syllabus, we are going to concentrate only on these two, logit and probit models. In the next lecture, I shall go more into detail of the logit model.